Well, I guess most of you know me. I'm Kilian. I'm a third-year PhD student now at the Institute for Climate and Atmospheric Sciences here at Leeds. And I'm working in nowcasting and in general in dust. And what I'm presenting today is the first part of my PhD, which was focused on developing a nowcasting tool for dust storms. So I guess most, but not all of us here are from the atmospheric science background. So this is basically the extended version of a conference talk I gave last month. So it's very much focused on the weather forecasting application. If you don't know any acronyms or any terms I use, just interrupt me and ask. So this is about an image-based approach to nowcasting of dust storms by predicting SEVIRI desert dust RGB composites. So lots of funky terms in there. So it's something about images and nowcasting. Nowcasting, for my case, is short-term predictions of weather phenomena on time scales from now, from the present, to up to 6 hours into the future, based on observational data. And I do that for getting some information about dust storms using these SEVIRI desert dust RGB composites. SEVIRI is an instrument on the geostationary satellite, and RGB composites are a form of fancy visualization. I'll show you in a second. So before getting started with the technical stuff, let's see what's now. Let me show you a quick video of giving an impression what we're actually dealing with. So this is not over Africa now, this is over Arizona by a guy, please handle it. But you can nicely see what kind of event that is. So these are large-scale dust storms, which are triggered through high gusty winds, which are generated through outflow of thunderstorms, you could say. So they form very cold and dense air parcels, which can sink down to the surface rapidly and then spread out. And these cause these gusty cold pool events, and they can lead to large-scale dust emission and uplift, which can cause these massive dust storms in source areas of dust. And as you might see in a second, you don't see it yet. These things cause really low visibility, so they disrupt traffic and transport. It's not helpful to breathe in all these fine particles, and that makes them high impact weather. And with that, we're back at nowcasting. So dust storms are high impact events. For the Middle East, North Africa, the UN estimate is a loss of about 13 billion per year due to these dust storms. However, when we try to model that with conventional numerical weather prediction, we have some issues. So most notably, these dynamics, which produce these cold pools, these dense outflows of these thunderstorms, you could say, are hardly reproduced or are not sufficiently reproduced in numerical weather prediction, which is the operational standard still today. So this thing here, this graphic shows in gray observation data from a weather station in southern Algeria, and in red what a model would have predicted there. And we're basically missing this peak here in the month June to August, September. This is when soon there. And that causes a lot of dust, and we're basically missing that in the model. So that's important for the climate scale, but it's also very important for the weather scale, because we basically do not have good predictions for these storms on the short time scales. However, we can see those storms, and we have satellites which are in geostationary orbit, so they basically rotate around Earth with the same angular velocity as the Earth rotates around its own axis, and they always see the same section under them. And with that, we can observe dust storms in real time, and that's actually also assessed by, or accessed, these products are accessed by operational forecasters looking into dust. And the idea is if we can use these data for creating a short-term prediction of dust. So it actually makes an ideal application in satellite observation space. How can we see dust? So this is from this geostationary satellite called Meteosat. This is Meteosat second generation, which sits in the equator plane at 0 degrees east. So it should be somewhere around here. So it sees basically all of Africa. I'm just showing you the northern part here. And you can nicely see all the surface features. You can see like the clouds in white, the ocean in dark blue. You see where it's more greenish. That's all from the visible channel. So something which resembles what we would see with our human eye. And I can actually tell you we had a lot of dust activity here in the center of the image. You really struggle to see any difference. Even if we zoom in, you might see there's some hazy shades here, but there are also these grayish clouds, so you can't really distinguish what is dust and what is cloud and what is background. You might ask, why do we look at satellite data? Why don't we use station observations? Well, this is for the same date, so it's the 8th of June this year. And all these little boxes are symbols for the observed weather over the specific location. And you can see, if you just look at the distribution, and we have a lot of observations in Europe, we have some observations in the Middle East and along the coasts, but in the more central areas, hardly any observations from stations. It's even worse for radar, so there's virtually no radar coverage in Northern Africa and Western Africa. Yeah, so how can we use, we're basically relying on the satellites, and how can we use those to see better where there's dust? So yes, we have very sparse information. And this is where red, green, blue imagery, so RGB imagery, comes into play. The idea behind that is, with our human eyes, we can see in the wavelength range of a few hundred nanometers, so from 300 something to the 700s of nanometers. However, the instruments which fly in satellites actually have a way broader range of wavelengths where they measure. So for this instrument I mentioned in the title, it is SEVIRI. This is on this geostationary satellite that is from the hundreds of nanometers until the infrared, basically. And the idea is now to assign different channels than what we would see with our human eye to the colors which we see as red, green, and blue, which our brain would combine into an RGB image. And to do that with wavelengths which are characteristic for the features we're interested in. So in that case, it's dust. So this is a maybe a bit complicated slide. Let's just look at that thing here on the right. So this is a spectrum of brightness temperature, what this instrument would measure when it's looking at a spot over the surface. The black line here shows what it would measure in a pristine, non-dusty atmosphere, and the gray one shows what it would measure in a dusty atmosphere. And these dotted lines show the channels where the instrument measures. So basically under these three red arrows here. And what you can see is, if you look closely in here, that the channel around 10 micron is suppressed stronger than the adjacent channels with the presence of dust. And the idea is now to use this feature and compute differences between this 10 micron channel and the adjacent channels and assign them to red and green. And then we simply select blue channel, which gives us information whether it's cloud or not a cloud. So the blue channel is more or less constant because it saturates for most cases. If the cloud, it saturates on one side or it saturates on the other side, we don't have blue, or not as much blue if there's no cloud. And that gives us something like a two-dimensional color space, where dust is somewhere in the bottom right, where it's pink. We go back to the satellite images. So there we still really struggle to see any dust. And if we look into the RGB thing, you see a lot of pink color popping up where before we only saw these hazy shades in there. You also see like a lot of other features which you saw in the previous image. So it's dark red, blobs here are cold cloud tops, so cold because they're very high. Deep convective cells, which are forming thunderstorms, typically have very high cloud tops, so that makes them very cold. So we see them as dark red. We see a lot of light blue here. Light blue is, in that case, usually the surface. We see some differences in here, which come from different orography there, but also different surface types, different emissivities of the surface types. So it's quite a complex image. If we animate that, you can actually see that we can somewhat see whether there. So we see everything is moving. We see these red blobs here growing. This is sometime in the afternoon now when convection thunderstorms develop. You can see these features here moving towards Europe, and you see these dusty areas, these pink areas, also moving around. And this is a very helpful product if you animate it and look at it with the human eye. Yeah. And this is probably the easiest for seeing where dust is going, where we currently have dust. And yeah, if we can create something like a prediction of such a product or the underlying data, it can be really useful for warning people there's something approaching, if there's something coming. And that is the central part of my work. Let's see. Yes, exactly. So looking for a way to predict these RGB composites showing the dust or the underlying data for creating these composites. When I started out with that project, I had a look into more conventional approaches based on optical flow, based on simple deterministic unit, giving a series of images in and predicting a series of images. But it all was not so super successful. And in the end, I ended up with looking into, more or less state-of-the-art generative models. So seeing this whole thing only as an image generation task or image prediction task, and not actually caring about the colors in the image. So we saw there's pink, which shows dust, there's dark red, which shows high and cold clouds, but I don't really care about these things. I just care about predicting the next frame, and then we can see what we can do with that. So looking at what other people are using for generating images these days, you immediately bump into all the diffusion model-based solutions, Stable Diffusion, DALL-E, Midjourney, and so on. Also, when looking more into weather forecasting, Google published that paper earlier this year with the GenCast, so their most recent development for weather forecasting. I think the Guardian even had an article last week or the week before claiming that the GenCast outperforms the ECMWF ensemble, but I haven't read it myself. But that is what we're sticking with now, a form of diffusion model for generating next frames of this composite image. So what is the basic idea behind diffusion models? So this is kind of based on ideas from non-equilibrium thermodynamics and some fancy math, so-called stochastic differential equations, which we can use for expressing a diffusion process, basically. How we can visualize or imagine that an image space would be, we have an image and we inject a form of noise, in that case Gaussian noise, into the image. I do that many times. It's basically a discrete diffusion. Then we inject noise until we have an image which has so much noise in there you can't distinguish it from a pure random noise field. And the idea is now that we can reverse this process, so we can reverse this equation basically and learn how to go back from the noisified image back to the clear image. There are multiple ways to implement that. In my case, I'm doing it with a, say, most simplistic version in image space, where the model is given the information of the step, basically, where we are, how much noise we, how many steps we already added noise, and how the denoised image should look like. I do that with many steps which add noise, and the model learns how to remove that over many different images. And in the end, we end up with a model which has learned something about how to remove noise from an image. So this is, in my case, implemented as a unit. A unit is often chosen for this kind of diffusion model. And the idea is then that we can condition this process. So during training, of course, we condition, but then we sample a random noise field, give the conditional input, and denoise this random noise field until we reach our data. So this can be used for simply reconstructing data, but yeah, given the conditional input, we could also generate like a sample which matches the conditional input in the way that it's a following frame, basically. So what you see here visualized then is we basically give the random noise sample in plus the conditional input, run it through the trained unit, and that predicts the noise, which should be subtracted from the initial noise sample for getting the slightly denoised frame. And we run that many times, and each time we predict the noise field, which we subtract from the previous slightly denoised image until we get the image. This is somewhat computationally expensive, but yeah, more about that later. So how does the processing chain and the data look like in my case? So I'm taking data from 2 years. It's about 70,000 frames, split that in 80% training, 20% evaluation. And my input then are these 3 channels, which form or which go into the dust RGB composite. I take the past 3 frames, so I have 9 grayscale frames in total, basically, and I stack them all together. And well, I don't directly stack them, I actually compute differences. So I basically put in the channels which go into the R, D, and the B, but the normalizing is only done with max min at that stage, and the final cutting to get that is in the last section. So that goes into the pre-processing. It's all stacked together for conditioning, and together with the noise sample, we compute the next frame of those brightness temperatures, so differences between the channel which goes into red, green, and the bare blue channel. We compute one frame that goes back into the model. So we basically sample recursively until we have the number of frames we actually want to predict in that. On the last frame, we simply generate the RGB images from the predicted data. How that then looks like, you don't see because just don't play here. So I should play here. Yes. So on the left, it's an observation. This is the day leading to the image you saw in the very beginning. On the right, it's the prediction. So the first 3 frames are the input data, these 3 frames, and now there's 12 frames, so 3 hours, that is, of prediction. And if you focus at most prominent features here, these dark red blobs, you see those show pretty realistic swellings. So the thunderstorms are basically growing, they grow deeper, they grow in extent. And you also see that these big areas here are moving. So this looks quite good for the moment. However, we see that the pink areas here are not as sharp as in the in the actual observation, and they also lose some intensity in the edges. So it's not ideal yet, but it definitely does something which looks very much like the observation. What else we can do? Stay on this thing here. So if we draw different noise samples given the same conditional input, we'll get slightly different realizations in our prediction. So this is for 8 frames, so plus 2 hours, plus 120 minutes in the future from initialization. Top left is the observation. All the others are different realizations which were generated with drawing different samples of noise, denoising that given the same conditional input. You might not see that much here, but if we animate that, so on the left again the observation, on the right the prediction, you see that there is quite a bit of difference between these different realizations here. So you see the red blobs here, the thunderstorms, basically they show slightly different extents, but you also see these pink areas here. The dust storm has propagated further, or it has not propagated that much. In some frames we get this cloud band here west from the pink area reproducing, which is actually a very common meteorological feature, whereas in others it does not do that. But it definitely looks like there is a reasonable spread in there. If it's realistic, is to be assessed. But that's already quite promising, at least at that stage. So a few slides about your evaluation of that. Well, so far I've only shown you animation of these different predictions, but actually for operational forecasting, we care about how good the product is in terms of predicting the features we're interested. So these are mostly the thunderstorms, the red blobs there, and the dust, which is pink color. And for looking into those, we apply some rather simplistic feature detection. So we simply look at everything which is very cold, so very dark red in that color, or which is anomalously pink, and call the former cold clouds and the latter dust. And we do that. We select features, so we basically get binary masks. We take that from all ensemble members and we average over the ensemble. We get something like this. So on the left, the cold clouds, on the right, the detected dust, dark red, and this is anomalously pink. And left again, observation, right, the prediction. And you can see we actually get something which looks very similar. We have some values between 0 and 1 at the edges in particular, which makes sense concerning the uncertainty of how fast these systems are developing and the exact propagation. And similar for the dust. However, for the dust, everything looks much more the detection of what is anomalously pink is actually not that trivial, because it involves basically looking at a deviation from cloud screens, so cloud-free background values and so on. So this probably introduces quite a large double panel, but it looks like it's doing something reasonable. We look at some back here. We look into some validation. So this is now evaluation over multiple months. So first 6 months of this year, it's about 4,000 nowcasts at a resolution of 128 by 128 pixels with an ensemble size of 11 members. We predict up to 6 hours into the future. And when you look at this area here in West Africa, for a rough idea how long that takes to compute, so one frame on a A100 GPU takes about 20 seconds. If we compute an ensemble of 11 members, it takes much longer. And if we go to higher res, at least with that model, it takes even longer. So the crucial thing here is that we actually must be much faster than reality, because we want to use that for short-term predictions in real time. And the satellite is scanning every 15 minutes, basically. And we want to be at least as fast as the satellite, because otherwise it would be not faster than real time, right? So we really want to be fast, but at the same time, if we want to do some probabilistic assessment of the prediction, we need an ensemble. So this should be somewhat balanced. Looking into skill of the ensemble, so this is fractional skill score. I'm not sure how familiar people are with that. Basically, it takes binary masks of a feature in the observation and in the prediction, and compares in different box sizes how many points in that box are true or are false, and compares it to a reference. As a rough baseline, I've included persistence. The persistence are the dashed lines. That is for simply taking the last observation frame, saying that is the prediction. And the solid lines are the nowcast. And what is considered as skillful is above 0.5 for that metric. So everything above 0.5 we usually consider skillful, and higher values are better. And what you can see is that for most scales, the scales is the box size in which we look at both feature masks, we see that the model outperforms persistence on most scales. On the final scales, that is for almost 4 hours into the future, and for the coarser scales, well, it varies a bit. For the very coarse scales, it's actually around 3 hours, but for the intermediate scales, we get something on the between 4 and 5 hours. So it's definitely more skillful than simply looking at the last observation for cold clouds. And for dust, that looks even better. So there's some value in looking into projected RGB imagery. Also looked at some rock curves. So these things look quite blocky because we have basically only here in the very low false positive rates we have values. However, those are also above the diagonal. If we look at the area under the curve, which is a common thing to look at skill, then can look into diurnal cycles of those. So in dashed or in dotted, it's the cold clouds, and in solid, it's the dust forecast. The dust is only for daytime, so we say from 6 a.m. to 6 p.m. since the dust detection or the pinkness anomaly detection has quite a strong diurnal cycle, and that would mess things up at night. We only look at daytime dust, and we look at clouds. What you can see for the clouds is we have this dip in skill basically in the afternoon. We see most convective systems, so storms growing, indicating that the model might not be good at, let's say, placing new storms. However, it's rather stable during night and in the morning, with higher skill in the morning when we have less thunderstorms developing, indicating that growing systems which are already there is less of an issue for the model. For dust, we see a pattern which is somewhat similar, with lower skill in the evening. This is also where we see most new pink areas, so new dust storms popping up. However, we get propagation, so dust storms moving around at all other times of the day, which works quite well with the model. And this morning peak is still a bit morning drop, actually. It's quite strange, you might think, but from everything I've seen, this is simply an artifact from the pigment detection, since we have a color cycle in the image, and in the morning the image simply has slightly different color than at later times of the day, and it doesn't work well with comparing it to observations for validating a nowcast or a forecast, which was initialized with slightly different colored imagery. So this much about metrics, a comparison with other methods. So I mentioned at the beginning, I looked into optical flow. I looked into deterministic nowcasts using a UNet. So these are the nowcasts generated with those methods in comparison with that diffusion model here. And you can nicely see the diffusion model. It shows quite a clear image compared to the observations, much clearer, less blurry compared to the deterministic UNet. And you see that we can actually also predict all those things here, which are growing. So especially these convective cells, they are somewhat missing in the optical flow method because it only moves around things which are there, and would not put in new convective cells or so. So this looks quite promising in the way that we can generate complete image, including other features than dust or the clouds, but also the color cycle somewhat, and it's much sharper than previous methods. And concluding, this nowcast can be used for predicting dust storms. It works for these convectively generated dust storms, which I've shown you in the beginning, which are commonly missed by the conventional numerical weather prediction. And it offers advantages by predicting complete images, including features besides dust, so most notably convective systems. And pairing that with feature detection allows us to generate a probabilistic nowcast. This has not extensively been evaluated yet, but it's definitely something one could still look into. Also considering that this approach could be used for nowcasting other composites, most notably that would be the convection composite, possibly also for ash, and a few next steps. What would be the obvious things to continue here with. So far that diffusion process is implemented in the image or the pixel space. The most obvious thing would be moving that into latent space, because we can save a lot of computational resources with that. Potentially also make the model a bit more stable. Working on better implementing information from past frames could be done with more elaborated conditioning stacks. So far, I'm just throwing all together the past frames. That could probably be much improved. And what could be really interesting, which I will actually do soon for a project in Southern Africa, is running that model live and seeing how that actually works with live data, and also getting feedback from people looking at those products. Thank you.
Thank you very much. Does anyone have any questions?
The uncertainty contained in this ensemble, how do you interpret that?
How do I interpret the?
As in this, is it really just the probability of dust at a single location?
No. No. So far that is simple. So it's simple ensemble of images. There's no calibration involved so far. I can actually, exactly show you that one here. So I checked some how that compares the predicted probability with the actual observed occurrence of those features. So blue is cold clouds, orange is dust, and you see that the model, with the way it spreads the different members of the model, is quite overconfident, basically. Right? it tends to say yes or tends to say no. It doesn't have much in between, and it's more confident than we actually see in reality. So if you want to use that operationally, you probably would need to control the spread in those onwards.
But is it theoretically? Is there a theoretical interpretation as well? Diffusion model.
You mean for like actual for application for weather? Yeah?
No, I don't know enough about it. I think, but like in my head, it seems like there could be a kind of natural probabilistic.
There might be. I'm not deep enough into the theory, I guess. I can just tell you with the spread we get from simply drawing random samples and giving the same input, we do not yet get a realistic spread which matches real world. Yeah.
Any elements of overlap between those big red patches if you had this cloud like above these pink areas? 'Cause I don't come from a weather background, but I was just wondering if there's any problems with that.
Well, it's in fact quite critical that in the way that pinkness usually appears next to dark red. Because these dark red things are thunderstorms, and out of these systems there's cold air flowing out and generating these dust storms. So
yeah, because in the YouTube video you see this big cloud of the storm. No?
Exactly, and you also get like some form of clouds at the leading edge of these pools. Often these are quite characteristic features. I think it's not so much an issue that these things happen next to each other. Right? It's kind of the blue channel which makes those things look different. It either separates in one or the other direction. So you have more blue in there. What comes an issue for longer lead times is some runaway effects. So when you get some color drift in the different channels, that even in the blue channel alone, that everything blurs, right? Or everything becomes darker or lighter, and then you can hardly distinguish what is what. Yeah.
There's a question online that says, "Thanks, that was interesting. One advantage of your approach seems to be that you don't need to know anything about physics. How do your predictions compare with physics-based methods?"
I'm not aware of any physics-based methods for dust storms, nowcasting dust storms. I've looked into the optical flow, which is, well, not really physics-based, but it has this element of simply forward projecting flow, which we already see. It performs better for that, for I think in all cases I looked into, but I haven't created like an evaluation on a large scale. In terms of comparison to NWP, numerical weather prediction, which is physics-based, it's basically not comparable, because if we miss the code pool in the numerical weather prediction, we don't get dust storm. So anything is better than that for these kind of storms.
Any more questions?
Is there another reason? Because you had this graph of all the different channels and they had peaks at different points. Is there a reason you chose the 3 peaks that you did and not some other peaks further down the spectrum?
This one here?
Yeah, like why not?
It's a common product. It's the common product generated from this satellite, but also other geostationary satellites sitting over the Americas and over Asia. They have similar channels, and they use these channels for creating this product where dust appears pink. So it's somewhat conventional, but it's also based on the let's say, on the assumed spectral characteristics of typical dust. Not all dust has the same characteristics, so yeah, you get slightly different spectra and also slightly different looks and images, but it's somewhat negligible compared to dynamics we see.
Do you find that your model favors certain values in its images that it generates?
I spent quite a lot of time looking into how to normalize my data.
Yeah.
Yes, because at first I started out with normalizing min-max, and I cut off some part of the edges, and at some point I ended up with a model which appeared to do something useful for clouds, but not for dust. And I think that simply was because the how to say, the spread in values you see in, you most commonly see in the images is much larger for the blue channel, which mostly shows cloud and no cloud.
Yeah.
Than for the red and green channel, which mostly shows the fine details of where dust is moving. So I had to tune that quite a lot, and I ended up with actually cutting off more the edges of the distribution during the normalization, but not as much as what is cut off for generating the RGB image, for actually retaining some information at the edges, basically. But yeah, that is crucial, and one might generate something which at first sight looks reasonable, but then you see, well, it does something useful for this channel, and the others look okay, but it doesn't have enough, yeah, those channels. So yes, that's definitely it. Keep in mind. I'm not aware of any convention or so for normalizing RGB imagery for such applications. So it was very much a try out and see what it does.